Welcome to this tutorial on industrial instrumentation. Today we'll talk about temperature measurement part 7 and we'll discuss thermistors. The topics that we will discuss in this tutorial are thermistor principle, then we'll discuss Steinhart-Hart equation, thermistor configuration, thermistor pros and cons, and the comparison between RTD, thermocouple and thermistors. The thermistor is the third type of electrical temperature sensor after RTDs and thermocouple, and they are thermally sensitive resistors and they exhibit large, predictable and precise changes in electrical resistance when subject to a change in temperature. The thermistors are made up of specific mixtures of pure oxides of nickel, manganese, copper, cobalt, iron, titanium, and other metals sintered at 982 degrees Celsius and above. Sintering is the thermal process of converting loose, fine particles into a solid, coherent mass by heat and or pressure application without fully melting the particles to the point of melting. Most thermistor sensors are NTC, that is negative temperature coefficient based. That is, their resistance value decreases with increase in temperature, while a handful of them have PTC or positive temperature coefficient. PTC thermistor major material is barium titanate given as BaTiO3, while NTC thermistor major materials are manganese, nickel and copper. Two stark differences between the thermistors and the RTDs are that while RTDs use pure metals as the sensing element, thermistors use ceramic or polymers, and secondly, RTD normally has a linear output scale for the better part of their range, while the thermistors are nonlinear temperature sensing devices. The temperature measurement range of the thermistor is from -100 degrees Celsius to 200 degrees Celsius, sometimes extended to 500 degrees Celsius under special conditions, with an accuracy of plus minus 0.1 degrees Celsius. Their resistance changes from 0.4 ohm to 75 mega ohm. The thermistor sensor is placed in one of the legs of a Wheaton bridge circuit, and the bridge imbalance gives a precise indication of the change in resistance value due to the change in temperature. Ra, Rb and Rc are the three fixed resistance values, where Rs is the thermal resistance due to the thermistor as in the bridge circuit. The change in resistance value due to change in temperature is numerically given as in equation 1, and a modified version is given in equation 2. The device sensitivity is calculated as shown in equation 3. Here we see that the change in resistance due to the temperature change is exponential and therefore nonlinear in nature. The value beta is specific for specific thermistor composition. The Steinhart-Hart equation is an important equation in context of thermistors, and it expresses temperature as function of thermistor resistance. Thus, if we know the thermistor resistance value, we can successfully determine the temperature. The Steinhart-Hart equation is given as 1 by T equal to A plus B log natural R plus C log natural R cube, where A, B and C are Steinhart-Hart equation parameters and R is the resistance at T degrees Celsius. The Steinhart-Hart equation is useful over the entire working temperature range of the thermistor. Just like the RTD, the thermistor also has three types of configurations, that is 2-wire, 3-wire and 4-wire configurations. In the 3-wire and 4-wire configurations, the additional wires, that is the third wire in the 3-wire and third and fourth wire in the 4-wire configuration, are used to connect to the exciting or the heating source. The 3-wire and 4-wire configurations lead to a high impedance path along the measurement device and thus effectively attenuates error caused by the lead wire resistance. Thus, they give more accurate results than the normal two-wire configuration. The advantages that a thermistor device offers are that the thermistor is the most sensitive device amongst RTD, thermocouple and itself. It has smaller size than thermocouple and better speed of response than the RTD. The thermistors are very good in terms of reliability, repeatability and stability. They are also very easy and convenient to use. The cost involvement for the sensor to set up is significantly moderate. On top of this, the thermistors have very good adaptability towards its surrounding conditions. There are, however, two major limitations of the thermistor, and they are: firstly, the device gives highly nonlinear and exponential measurement, and secondly, the device has the smallest temperature measurement range, ranging from -100 degrees Celsius to a maximum of 500 degrees Celsius under very specific conditions. Here we draw a comparison between the three main types of electrical temperature measurement devices, that is the RTD, the thermocouple and the thermistor. The properties on which these three devices are compared are their range, cost, stability, accuracy, sensitivity, linearity and objective purpose. We see that the thermocouple can measure both the highest and the lowest temperature and has the widest measurement range from -270 degrees Celsius to about 2600 degrees Celsius, while the thermistor operates in the slimmest temperature range. The thermistors are mostly nonlinear in nature, but they have the distinctive advantage of highest sensitivity and pinpoint measurement, and operational capabilities in narrow temperature ranges. The RTDs offer the best measurement stability and accuracy. Viewers can refer to the following links and references for more detailed study. Thank you.